All right, let's dive right in. In this explainer, we're going to uncover some really strange and beautiful geometry that's hiding in plain sight, right inside the heart of all modern electronics. So let's start with this. You're looking at a diagram of something you've probably never actually seen before, but literally billions of them are working for you this very second. It's called a MOSFET, and it is, no exaggeration, the single most manufactured object in all of human history. It's the fundamental building block of our entire digital world. Now, before we get into the wild world of fractals, we really need to get a handle on what this tiny little device is and, what it actually does. Okay, so a MOSFET, and that's a mouthful, it stands for metal oxide semiconductor field effect transistor. When you boil it all down, it's basically just a microscopic switch. The best way to think about it is like a tiny, tiny dam that's controlled by electricity. It can either stop the flow of electrons or let them rush on through. Here's how it works. You've got a source, that's where the electrons are coming from, and you've got a drain, that's where they want to go. In between them is this channel, and sitting right on top of that channel is the gate. Now, when you zap the gate with a tiny bit of voltage, it creates an electric field that opens the channel. It's like opening the floodgates of the dam, and boom, current flows. Turn the voltage off, the gate closes. Simple, right? It's a binary switch, on or off. 1 or 0. So for decades, the name of game in the tech industry has been almost brutally simple. Just make these switches smaller, and then make them smaller again. Because the more of these things you can cram onto a single chip, the faster and more powerful our computers get. You've probably heard of this relentless shrinking, right? It's called Moore's Law. For more than half a century, it's been the engine driving our entire technological revolution, basically saying that the number of transistors on a chip will double every couple of years. But there's a problem, a big one. As we shrink these switches down to just a few nanometers across, we're talking about nearing the size of individual atoms here. We hit a wall, a quantum wall. The predictable, classical rules of physics that engineers have relied on for so long, they just break. So welcome to the quantum realm. Down at this tiny scale, electrons stop acting like predictable little billiard balls. Instead, they behave like these fuzzy waves of probability. You can't really pin them down anymore. And when you confine them in such a small space, their energy can only exist at specific, separate levels. The old rulebook is officially out the window. This quantum weirdness means that our old models, our old blueprints for designing transistors, are completely useless. It's kind of like trying to use a map of New York City to find your way through the Amazon rainforest. It just doesn't work. So scientists needed a new map, a whole new kind of math, for this very strange new territory. And believe it or not, the answer they turned to is this fascinating and kind of beautiful branch of math, fractals. You've definitely seen these before, even if you didn't know the name. They're in the repeating patterns of a snowflake, the jagged edge of a coastline, even in the branching of a head of broccoli. They are patterns of infinite, repeating complexity. And this isn't just some wacky idea they pulled out of thin air. The research itself points out that at the nanoscale, materials don't really form smooth, perfect surfaces. They naturally tend to assemble themselves into these complex, fractal-like shapes. I mean, the jaggedness is already there. We just needed the right math to describe it. So here's the big what-if moment. What if we stop trying to model the space inside a transistor as being all smooth and simple? What if instead we embrace its natural messiness and treat it like a fractal space? A space that doesn't have a simple dimension like 1D, 2D, or 3D, but something weird, in between. Okay, so this leads us right to the core of the research. If the space inside this tiny switch is a fractal, then it has to have a fractal dimension. The question is, what is that dimension and what does it tell us about how these things actually work? Right? So that's the million-dollar question, isn't it? The researchers took their new fractal model, applied it to the super complex equations of quantum mechanics that describe what's going on inside the transistor, and they were able to zero in on a very, very specific number. And here it is, approximately 0.66. Now, this is not just some random number they pulled out of a hat. This is the effective fractal dimension of the space that an electron experiences inside a quantum-scale transistor. You can kind of think of it as a measure of how space-filling the electron's path is. It's more than just a single point, which has a dimension of 0, but it's not quite a full continuous line, which would have a dimension of 1. It's somewhere in between. Now this graph, this is the proof in the pudding, right here. It shows us why that number is so important. For most other fractal dimensions you could plug in, The math just breaks. See how the lines shoot off to infinity? That's physically impossible. But in this very narrow window between about zero point 0.5 and 0.67, the model suddenly becomes stable. And our number, 0.66, is sitting right in that sweet spot, giving us a model that actually works, one that reflects reality. Okay, so we've got a new number, we've got a new model. That's some cool math, but why does this actually matter? What does a weird number like 0.66 mean for you or for the next phone you're going to buy? Well, this is a huge deal. Having a more accurate map of this quantum world means engineers can design the next generation of computer chips with way more precision. It could help keep Moore's law alive a little bit longer, but the impact goes way beyond your laptop. This fractal way of thinking could lead to major breakthroughs in things like supercapacitors for faster charging batteries, and even more efficient solar cells and LEDs. So when you boil it all down, the big idea here isn't just about the math. It's about finding a brand new lens, a new way of seeing the fundamental building blocks of our modern world. By embracing the complexity, the inherent jaggedness of the nanoscale, we can learn to predict it and engineer it better than we ever could before. And that really leaves you with a fascinating final thought, doesn't it? If the very heart of our most advanced technology is secretly being governed by these beautiful, complex, fractal patterns, what other secrets are out there just waiting for us to find them, hidden in places we always thought were simple and smooth?